Imagine you're using your favorite text editor and just made a mistake. You instinctively press Ctrl-Z and the error disappears as if it never happened. But have you ever wondered how that undo action works? Do you know what's happening behind the scenes when you correct your mistake with a single keystroke? By the end of this video, you'll understand the practical applications of stacks. And having studied the complete lesson, you'll understand how stacks are used in 3 key areas: managing function calls in programming, converting expressions from infix to postfix, and implementing undo mechanisms in software. In Java, a stack is more than just a concept. It's a data structure implemented with its own dedicated class called stack. This means that when you create a stack in your Java program, you're essentially creating an object of this stack class. This stack object comes equipped with a set of methods specifically designed to manipulate data. At their core, stacks operate on this last in, first out, or LIFO principle. To understand LIFO, imagine a stack of plates at a buffet. When you stock up the plates, you add a new plate on top of the stack of plates. If you need to use a plate, you remove the top plate first. The plate at the bottom stays there until all the plates above it are removed. Stacks work precisely like that. You push data onto the stack, and when you need to retrieve it, you pop the most recent data off first. This behavior makes stacks incredibly useful in scenarios where you must keep track of actions or tasks in a specific order and revisit them in reverse. But how does this abstract concept of stacks translate into something practical in the programming world? Let's explore one of the most fundamental areas where stacks play a critical role in function calls. Have you ever wondered how a computer knows where to return after calling a function? Here's where stacks come into play. When a function is called, the code's current position and local variables are pushed onto the stack. The function then executes, and once it's done, the program pops the return address off the stack and jumps back to where it left off. This process ensures that the program can handle multiple nested function calls and return to the correct point in the code each time. Without stacks, keeping track of these return points would be chaotic and error-prone. The initial call is add 3 and 2. The stack starts with add 3 and 2 as the top and only element. The first recursive call is add 4 and 1. Therefore, add 4 and 1 is now pushed onto the stack, becoming the new top element. Add 3 and 2 remains just below it. The second recursive call is add 5 and 0. Add 5 and 0 is pushed onto the stack, becoming the new top element. The previous top, add 4 and 1, is now just below it. Returning from recursive calls, as add 5 and 0 hits the base case y equals 0, it returns a value, and the stack begins to unwind. Add 5 and 0 is popped off, making add 4 and 1 the top element again, followed by add 3 and 2 as the stack continues to unwind. Next, let's talk about expression evaluation, particularly converting infix expressions. For instance, 3 plus 4 multiplied by 5 to a postfix notation like 3, 4, 5 multiplied sign, addition, sign. This might sound complex, but it's a critical process in how computers evaluate mathematical expressions. In infix notation, operators are placed between operands, which can lead to ambiguity in the order of operations. To simplify this for computation, the expression is converted to postfix notation, where the operators follow the operands. Stacks are the perfect tool for this conversion because they allow us to temporarily store operators and ensure they are applied in the correct order. By pushing and popping operators at the right moments, the stack helps us rearrange the expression into a form that's easy for computers to evaluate. Starting with the infix expression, 3 plus 4 multiplied by 5, where operators are placed between operands. Operator precedence can complicate the evaluation, so converting to postfix notation simplifies it. Now, let's take a look at this conversion, step by step. First, the operand 3 is encountered and goes directly into postfix expression. Next, the plus operator appears. Since the stack is empty, plus is pushed onto the stack. The next operand 4 is added directly to the postfix expression. Now, the multiply operator is encountered. With higher precedence than plus, multiply is pushed onto the stack above plus. The final operand, 5, is then added to the postfix expression. With no more operands left, the stack proves its usefulness. Operators are popped in the correct order. First, multiply, then plus, ensuring the postfix expression is properly formed. The final postfix notation is 3, 4, 5 multiply plus. Thanks to the stack, the operations are organized in the correct sequence without needing to consider precedence directly. That's how the stack makes converting infix to postfix easy. It uses its LIFO order to automatically figure out the right order for math operations. Finally, let's understand stacks through the undo mechanism mentioned earlier. Whether in a video game, text editor, or other software, the ability to undo actions relies heavily on stacks. Every time you act, the software pushes a record of that action onto a stack. If you decide to undo the action, the software simply pops the most recent action off the stack and reverses it. Stacks are ideal for managing a history of actions because of their LIFO nature, allowing you to backtrack step by step. Actions are added to the stack from the bottom up, with each new action placed on top. During an undo, actions are removed from the top down in reverse order. Stacks are everywhere, from the books in the library to the software we use daily. By understanding how they work and recognizing their use cases, you can see the power of this simple yet effective data structure. Whether you're managing tasks, navigating through web pages, or coding, stacks provide an organized way to handle data and operations efficiently. Embrace this concept, and you'll find yourself better equipped to tackle various challenges in both programming and everyday life. Imagine this. You're in your kitchen, stacking clean plates after washing them. Naturally, you place one plate on the other, making a neat stack. And when it's time to grab a plate, you don't reach for the bottom one. You pick the one on top, right? Well, that's exactly how a stack works. In this video, you'll explore the concept of stacks, one of the most important data structures in programming. By the end, you'll know what a stack is, how it operates, and how to use its basic functions. So what exactly is a stack? It's a data structure that works on the last in, first out, or LIFO principle. You've already seen this in action with your plate stack. The last plate you put on the top is the first one you take off. Stacks in programming work precisely like that. But before we go deeper, let's quickly define a linear data structure. This type of data structure has elements arranged in sequential order. Think of it like a line of people waiting to get into a concert. Each person stands in a specific order, one after another. Stacks aren't just a theory, however. They're used all over in programming. For example, when your browser lets you click back to return to the last page you visited, it's using a stack. Or when you're undoing a mistake in a document, same thing. Understanding stacks can help you recognize these patterns in everyday coding. Now let's get into the main operations that make a stack tick. There's push, pop, peek, and isEmpty. They sound simple, but they're also super important for managing data in a stack. Let's break them down. First up is the push operation. This is when you add an item to the top of the stack. Picture adding a plate to your stack of plates. It goes right on top, becoming the new top of the stack. In coding, when you push an item, it becomes the top item in the stack. To see how this works, imagine your stack of plates. Picture an empty stack where you first place plate 1. Then, plate 2 goes on top of plate 1. Finally, you'll add plate 3 on top of them all. As you'll see shortly, the last plate you added, plate 3, will be the first removed in a pop operation. This is how stacks follow the last in, first out principle. Now, what if you need an item? Then you pop it off the stack. The pop operation removes the top item from the stack. Just like grabbing the top plate, the last item you added is the first one to go. This operation usually gives you the removed item as well, so you can use it in your code. Let's return to the stack of plates. You have 3 plates in your stack, plate 3, plate 2, and plate 1. When you pop, plate 3 is removed first, followed by plate 2, and finally plate 1. Now the stack is empty. What if you don't want to remove the top item, but just want to see what's there? That's where the peek or top operation comes in. It lets you take a quick look at the top item without popping it off the stack. It's like glancing at the top plate to check if it's the right one. Let's return to the plates. If you peek when there's only one plate, you'll see plate 1. Now, if you push plate 2 on top and peek, you'll see plate 2. Finally, if you push plate 3, a peek will show that plate 3 is now on top. So with the peek operation, you get to see the top item without making any changes to the stack. In a stack data structure, peeking is useful when you need to know the top or most recent element, but want to keep the stack unchanged. Finally, there's the isEmpty operation. This one's handy when you need to check for any items left in your stack. When you run this operation and the stack is empty, it returns true. If not, it's false. Simple, right? It helps avoid errors, especially when you try to pop or peek at an empty stack. For example, in your plate scenario, you start with an empty stack. After pushing plate 1, the stack is no longer empty. The more plates you push, the more items the stack has. But before that first push, isEmpty would return true, meaning the stack has no elements yet. So, that's a stack in a nutshell. Just remember the last thing in is the first thing out. Elements are pushed onto the top of the stack and popped off from the top, just like how you'd handle a stack of plates. Remember this and you've got the essence of stacks. Keep practicing these concepts because they're foundational in programming, and you'll see them pop up, pun intended, in more advanced topics down the line. Imagine you're developing a web browser's history feature, where each new page visited gets added to the top of the history list. To manage this effectively, you're considering using a stack. But how do you choose the right implementation for your stack using arrays or linked lists? Each choice impacts how efficiently the browsing history can be managed, especially regarding time and memory usage for different types of users, from casual browsers to power users visiting hundreds of pages. In this video, you'll explore the time complexity of stack operations in an array-based implementation. You'll also compare linked list-based and array-based stack implementations, focusing on their flexibility and memory usage. Finally, you'll gain an understanding of the trade-offs involved in choosing between these two common implementations. Let's get started. Stacks can be implemented using arrays or linked lists. Both implementations adhere to the last in, first out, or LIFO principle, but they differ significantly in handling tasks like pushing, popping, and peeking. It's important to understand these differences when choosing which method to use in different situations. Let's start with the array-based implementation. In this approach, a stack is implemented using a fixed-sized array. Here's a breakdown of the key operations. Imagine your stack as a row of boxes. It currently holds 3 items, 20, 40, and 60, with 60 on top. When you push 80 onto the stack, it gets added to the next empty spot, which is at index 3. Now, 80 is the new top item, sitting on top of the stack. If you just want to check what's on top without changing anything, you peek. Right now, peeking shows 80, the top item. It's like looking inside the top box without taking it out. When you pop the stack, you remove the top item, 80. After popping, 60 becomes the top item again, and the space where 80 was is now empty. Let's examine the pros and cons. Array-based stacks are straightforward and offer fast access to elements. The main limitation is the fixed size. Array-based stacks use the same sizing rules that you learned when working with arrays in Lesson 1. If the stack exceeds the array's initial size, resizing is required, which is costly in terms of time. Now let's consider the linked list-based implementation. In this approach, each element in the stack is a node in a linked list, with each node pointing to the next one. In this diagram, you'll notice the nodes are connected like a chain forming a stack. Node 1 points to node 2, node 2 points to node 3, and so on until the last node, node 4, which doesn't point to anything. When you push a new item onto the stack, a new node is created and linked to the current top. This new node becomes the top of the stack. If you pop the stack, the top node is removed and the next node in line becomes the new top. Peeking lets you see the top item without removing it. In this setup, peeking would show what's stored in node 4. Let's examine the pros and cons. Linked list-based stacks are dynamic and do not require a fixed size, making them more flexible regarding memory usage. The trade-off is that they require more memory per element due to the overhead of storing pointers, and they might incur additional overhead in terms of cache efficiency. Next, let's compare both stack implementations regarding flexibility and memory usage, starting with array-based stacks. Imagine you know exactly how many elements your stack will hold. In this case, an array-based stack might seem like a great choice. An array-based stack is simple, but limited to max size elements. If you exceed this, the stack needs to resize, which involves creating a new array and copying elements over, turning an order of 1 push operation into an order of n. The stack pre-allocates a fixed block of memory. If the stack doesn't fully use it, memory is wasted. Reallocating more space is costly in both time and resources. Push, pop, and peek are generally order of 1, but when the array is full and needs resizing, push becomes order of n, due to the time required to copy elements to a new array. Now, what if the number of elements in your stack is unpredictable? This is where a linked list-based stack shines. There's no predefined size limit. You can keep adding nodes as needed, and the stack will grow dynamically. This makes push operations consistently order of 1, regardless of the number of elements. Each node requires additional memory to store a reference or pointer to the next node. While this adds flexibility, it also increases the memory footprint compared to arrays, especially for large stacks. However, for very large elements, the overhead of pointers might become negligible. Push, pop, and peek operations are consistently order of 1 because they only involve updating or accessing pointers with no need for resizing. Array-based stacks are best when you know the stack's maximum size in advance and want to minimize memory overhead. However, resizing can be a costly order of n operation. On the other hand, linked list-based stacks are ideal for scenarios where the stack size is unpredictable. They offer great flexibility with consistent order of 1 time complexity for push, pop, and peek, but at the cost of extra memory for pointers and potentially lower cache efficiency. In this video, you learned that choosing between an array-based and a linked list-based stack depends on the specific requirements of your task management scenario. Consider the nature of the tasks you're managing when deciding on a stack implementation. Understanding the time complexity and memory trade-offs will help you make the best choice for your application. Imagine you're standing in line at a coffee shop. Everyone waits their turn, and the first person in line is served first. This simple concept of first come, first served is how a queue works. But did you know this everyday scenario is also crucial in how computers manage tasks? In this video, you'll explore the practical applications of queues, a fundamental data structure in computer science. You'll gain an understanding of how queues play a vital role in operating systems for CPU scheduling, handling I/O requests, and managing tasks like printer spooling. Finally, you'll delve into how queues are used in networking to manage data packets efficiently. Let's examine queues in more detail to learn more. A queue is a linear data structure that follows the first in, first out, or FIFO principle, similar to the line at the coffee shop. The first element added to the queue is the first one to be removed. This orderly approach is perfect for managing tasks where timing and sequence are critical. In contrast to stacks, which follow the last in, first out, or LIFO principle, queues ensure that elements are processed in the order they arrive. Like the coffee shop line, the first person to arrive is the first person served. Queues are used in various areas of computing to manage tasks efficiently and ensure that processes are handled in a fair and organized manner. Let's examine how the queue works in this coffee shop scenario. Here, person 1 is at the front of the line, so they're served first, as shown by the red arrow labelled 1. Once they're served, they leave the queue. Next, person 2 steps up, indicated by the yellow arrow labelled 2. They are served and then leave the queue. This process continues with person 3 and 4, following the arrows labelled 3 and 4. Each person is served in the exact order they arrived. This simple example of a queue demonstrates how tasks are managed efficiently and fairly. Now let's explore how this concept of queues applies to more complex systems, like operating systems, where they are essential for keeping everything running smoothly. Think of an operating system as the manager of a bustling office. It has to handle multiple tasks, prioritize them, and ensure everything is done in the right order. Here's where queues come into play. The CPU is like the barista in the coffee shop, taking one task at a time and completing it before moving on to the next. But in a computer, there are countless tasks waiting to be processed. A queue helps manage these tasks by organizing them in the order they arrive. For example, in a first come, first served, or FCFS scheduling, the CPU processes tasks in the exact order they enter the queue, just like the first customer in line gets their coffee first. While this is similar to the FIFO principle we discussed earlier, FCFS is a specific scheduling algorithm that applies the FIFO concept to CPU task management. Here, tasks line up in a queue: task 3, task 2, and task 1. The CPU processes them in the order they requested, following the FCFS method. Task 1 goes first, followed by task 2, and then task 3. This is known as first in, first out, or FIFO, just like customers in line at the coffee shop. Devices like keyboards, mice, and printers constantly send requests to the CPU. These requests are placed in a queue, ensuring each request is handled in turn. This prevents chaos and ensures no request is lost or ignored, like how everyone in the coffee shop line eventually gets their order. Here we have 3 devices: a keyboard, a mouse, and a printer. Each of these devices sends requests to the CPU. These requests are represented by the boxes labeled Request 1, Request 2, and Request 3. These requests don't go directly to the CPU. Instead, they are placed in a queue, which organizes them in the order they arrive. Notice how Request 1, Request 2, and Request 3 are lined up in the queue. The CPU processes these requests one by one, starting with the first in line, Request 1, and then moving on to Request 2 and Request 3. Imagine several people in an office sending documents to a single printer, one after another. Instead of printing everything at the same time, which would be impossible, the printer uses a queue to manage the print jobs. The documents are printed in the order they were sent, ensuring the output is organized and predictable. This management of print jobs is known as spooling, and it's a perfect example of how queues help manage resources efficiently. Here, 3 people, person 1, person 2, and person 3, each sent a document to be printed. The documents are labeled Document 1, Document 2, and Document 3. Instead of being printed simultaneously, the documents are placed in a queue. Notice the order. The numbers 1, 2, and 3 indicate the sequence in which these documents entered the queue. The printer processes these documents, one at a time, following the received order. Document 1 is printed first, followed by Document 2, and finally Document 3. Queues aren't just useful in operating systems. They also play a crucial role in networking. When data is sent over a network, it's broken down into smaller units called packets. These packets need to be managed carefully to ensure that they reach their destination in the correct order and without loss. Here's how queues come into play. In a network, data packets from different sources arrive at routers and switches, which direct them to their destinations. These devices use queues to manage the incoming packets, ensuring they are processed in the order they arrive. This orderly processing prevents network congestion and ensures data is transmitted efficiently and reliably. In more complex networks, some data packets might need to be prioritized over others. For example, a video call might need to be prioritized over a file download to maintain smooth communication. Queues can be used to manage these priorities, ensuring that the most critical data is handled first while less urgent tasks wait their turn. In this video, you learned that queues are everywhere in computing, quietly ensuring that processes are managed smoothly and efficiently. Whether the CPU schedules tasks, handles input-output requests, manages print jobs, or transmits data over a network, queues ensure that everything is done in an orderly fashion. Just like in a busy coffee shop, queues help keep things fair, organized, and running smoothly, ensuring every task gets its turn. Imagine you're driving in the city during rush hour. You stop at a traffic signal and, to your dismay, see many cars ahead. The light changes and the car at the front goes first, followed by each car in order. This sequence of movement is like a queue data structure in Java. In this video, you'll get an idea of what a queue data structure is, specifically a standard queue. You'll see a breakdown of how a queue works using the first in, first out, or FIFO rule, and compare it to a real-world example to help you understand. So, what is a queue exactly? A queue is a linear data structure that stores elements in an ordered sequence. Elements are added at the back and removed from the front. A queue follows a first-in, first-out principle that defines its operation, making it ideal for scheduling processes or handling asynchronous data. To visualize the FIFO principle, think about how cars line up at the signal. The first car to arrive is the first one to leave. In the same way, the first element added to a queue is the first to be removed. A queue supports two primary operations, enqueue and dequeue. Let's quickly look at each. In a queue, you use the enqueue operation to add an element at the end, like a car joining the back of the line. Dequeue removes the first element from the front, just like the car at the front of the signal drives away when the light turns green. In a queue data structure, the first element added, or enqueued, is the first one removed, or dequeued. Let's see this visually. Imagine a queue of numbers starting with 2 at the front and ending with 6 at the rear. To dequeue, you would remove the front element, which in this case is 2. 3 now moves to the front of the queue. To enqueue, you would add a new element, 8, to the rear of the queue. You may have noticed the terms front reference and rear reference in the image. These play important roles. The front reference indicates the position of the first element in line, in other words, the next car to leave the traffic. This indicates the element that will be dequeued, removed, next. The rear reference represents the position where the next element joins, in other words, where a car joins the traffic line at the back. In the queue, this is where the next element will be enqueued or added. The front and rear positions change as more cars enter or exit the traffic line. Similarly, when elements are added or removed from a queue, the front and rear references adjust to show their new positions. Keep in mind that a queue can't accept more elements once it reaches its defined capacity. This constraint depends on the queue's implementation, whether it's backed by a fixed-sized array or a dynamically expanding structure like a linked list. Now let's see how this works in Java. Let's first focus on the enqueue operation. When a new car arrives at a traffic signal, it joins the back of the line, just like the enqueue operation, where new elements are added at the rear and processed in order of arrival. In the code, the first step is to check if the queue is full using isFull. If it is, the process stops, and a message is displayed. Queue is full, cannot enqueue, in this case. If the queue isn't full, the rear index is incremented, and the new item is added to this updated rear position. Finally, the queue size is increased by 1 to reflect the new addition. Simple and efficient. Now let's focus on the dequeue operation. Here, the first element is removed from the front, like the first car to leave when the light is green. This process is critical because it keeps things running smoothly. Without removing the first car, no one else can move forward. If the car at the front stayed put, blocking everyone behind it, traffic would become chaotic. So, when the traffic signal light turns green, the car at the front of the line moves first, making room for the cars behind it to move up. This is how the dequeue operation works in a queue. The element at the front of the queue is the first one to be removed. In the code, first check if the queue is empty using isEmpty. If the queue is empty, a message is printed and -1 is returned. If not, the item at the front of the queue is stored and the front index is incremented to reflect the removal. The size is reduced by 1 and the dequeued item is returned. Great. Now you know how to use the enqueue and dequeue operations in your IDE. Now imagine you're in a long line of cars at a traffic signal, wondering how long the wait will be. You might peek ahead to see which car is at the front, but without moving or changing their positions, just a quick check to estimate when the light might change for you. In Java, you can use the peek operation to do something similar. Check the first element without altering the queue. This operation is useful in task scheduling to check the next task or data without modifying the queue or disrupting future operations. The code first checks if the queue is empty using isEmpty. If it is, it prints a message and returns -1 to show that there's nothing to peek at. If the queue isn't empty, it simply returns the item at the front without removing it or modifying the queue. Handy. In this video, you explored the concept of a queue as a linear data structure that follows the first in, first out principle. You observed how it can be compared to cars at the traffic signal, where the first car to arrive is the first to leave, and new cars join at the back of the line. Just like managing traffic flow, queues play a crucial role in many real-world scenarios, from task scheduling to resource management and computing. Keep practicing, and you'll see how valuable queues can be in solving problems.